Right, we start from the foundations of graph theory, the most basic of questions you can ever come across, the ability to draw graphs that are non-isomorphic. But first, we remind each other that two graphs, G and H, are called isomorphic. Are called isomorphic if there exists a one-to-one correspondence one-to-one correspondence. So now this is very important because this is the definition that we use all the time. So one-to-one correspondence between the vertices in G and the vertices, okay, and the vertices in H, okay, in H. Right, so we have that. Now, right in H. Right, okay. Such that a pair of vertices are adjacent in G if and only if the corresponding pair of vertices are adjacent in what? In in H. Right, so we just look at this definition, which is the most important. So two graphs are isomorphic. Right, so what is this thing that I've written here? What I've written here is actually the definition of isomorphic graphs. So two graphs, G and H, are called isomorphic if there exists a one-to-one correspondence between the vertices in G and the vertices in H, such that a pair of vertices are adjacent in G if and only if the corresponding pair of vertices are adjacent in H. Okay, so this definition here speaks of something that we need to take note of, but not just take note of this, but always. The idea of a one-to-one correspondence, is extremely important. So you need to learn these and be in a position to understand this. Okay, now what do we do and how do we manage this? Right, so now in this question, we need to draw three non-isomorphic graphs. So these are sort of the basic questions I'm beginning with on graph theory. Three non-isomorphic graphs with four vertices and three edges. What kind of a graph is this? What kinds of graphs are these and how can these graphs be drawn? So we look at these together and we We reason. Okay, here's a graph on 4 vertices. Vertex, vertex, because they're speaking of 4 vertices. Vertex, vertex. Okay, so we have those vertices there. And then now these vertices are 4 of them. And so what do we do? But we need 3 edges. So we're going to put an edge here. You can put an edge there. You can put an edge there. And so this graph obviously has 4 vertices and 3 edges. Now, but we need non-isomorphic, right? So the non-isomorphism is suggested by the degrees of the corresponding vertices. So now we can also do vertex, 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 so that we have 4 vertices. And then now we need to draw 3 edges, right? So we can draw 1 edge, second edge, and third edge. So there are 3 edges here, right? And yet there are 4 vertices for this graph, right? But we need to draw up to 3 of them. So we draw the third one, vertex, 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 vertex. So then what we do, we draw an edge here, for example, another edge here, another edge there, like this. So we agree, therefore, that we have these graphs are non-isomorphic. How are these graphs non-isomorphic? Right, so the 3 graphs, right, the 3 graphs are non-isomorphic. Non-isomorphic. Because, why? Because the first, because the first has 2 vertices. There's 2 vertices of degree 1. Okay, so we have this one vertex of degree 1 and that of degree 1 because there's one incident edge to it, right? And moreover, the second graph, this one here, you need to always substantiate. That is the point. Right, the second graph has no vertices. Right, so we need to just write it clearly here. Right, so the second graph, now we just compare, we just substantiate on why these graphs. So if they ask you to draw, it's very important to substantiate why the graphs you have drawn are either isomorphic or non-isomorphic, because they can ask you to draw either isomorphic or non-isomorphic. Right, so the second graph has no vertices of degree 1. So in other words, obviously you agree that this second graph, this vertex here is of degree 2 because there are 2 incident edges. This one is degree 2. So obviously this graph has 2 vertices of degree 1, and the other 2 vertices are of degree 2. But this one does not have even 1 vertex of degree 1. Okay, so the second graph does not have a vertex of degree 1. Right, so right, the second graph has no vertices of degree 1, right? And the
Hello.
third graph, let's come into the third graph.
Hello.
Yes, please.
In the exam, I only need to show this.
Yes, in the exam, you need to just draw. But ordinarily, you need to substantiate on why, depending on the case. But what is very important is the drawing. Okay, so, but obviously, by and large, if you draw, then you deserve all the marks. That is the point. If you draw, then you deserve all the marks. Right. So um, is pretty much enough because you're under exam conditions. Right. And the third graph, would have degree 1, degree 1, degree 1, degree 3. Right. So the third graph has um 3 vertices of degree, right? It has 3 vertices of degree 1. Okay, just some substantiation that if the graphs are were to be isomorphic, if this one is 2 vertices of degree 1, each one must have 2 of them, etc. So yeah, the drawings are the most important anyway, in particular under exam conditions. Right, but it is standard practice to draw and substantiate based on what follows from the drawings in terms of which graphs are actually in terms of whether the graphs are isomorphic and why will they be. But obviously at this point, it's not so important to, obviously substantiate quite anyway, in particular under exam conditions. Right, so let's look at one more question. You need to now, we're just practicing here on how to draw graphs, right? Given information in words. Like at this point, you're saying draw 2 non-isomorphic graphs with 5 vertices and 6 edges. Okay, 5 vertices. So first, normally we draw as if we draw a pentagon like this. Then you can join, join, join. Right, and then you can join, join. How many edges are here, for instance? So you can see there 2, 4, 5. So we just need one more edge. So we can connect like this because we need 6 edges and 5 vertices. So this one satisfies those conditions. Right. So we can also draw another graph. So we can draw 1 vertex, 2, 3, 4, and then do 5 here. We draw like this. We draw like that. We draw like that. We draw like that. So at this point, you have um, 5 vertices, 2, 4, 5, and obviously 3, 6 edges. Okay, so we have that. So in particular, we substantiate because we're learning on why we need to, because it helps us. The substantiation helps us to be in a position to understand the isomorphism of the graphs, but also to apply ourselves and be able to say when 2 graphs are not isomorphic, which is what is examinable. The next thing we're going to be looking at in the exam when graphs are given. So the 2 graphs, are non-isomorphic. Right. They are non-isomorphic. Why? They are non-isomorphic because, right, they are non-isomorphic because, right, so the 2 graphs are non-isomorphic because, okay, right, because the second graph, right, because the second graph has a vertex, is a vertex of degree 4. Okay, so in other words, there's this vertex, it is of degree 4. So that one is a vertex of degree 4. Okay, so we continue. Right, as a vertex of degree 4. Okay, we'll continue. We continue. Right, so now the second graph is a vertex of degree 4. Right, while the first graph. Um, okay, while the first graph. Um, right, while the first graph. Right, while the first graph does not have such a vertex. Right, the two graphs are non-isomorphic. They're not isomorphic. Why? Because this one is a vertex of degree 4, while the first graph does not have such a vertex. So it's enough to say the two graphs are not isomorphic, because if they ever they're isomorphic, then if there's a vertex of degree 4, you must have a vertex of degree 4 there. But most importantly, if you have the vertex of the just vertices of a certain degree in one graph, maybe this one, degree 2, degree 2, how many vertices of degree 2 here? There are 4 of them. Okay, so here you would expect to have 4 vertices of degree 2. All right, but obviously if you count degree 2, it's 1, 2, 3. Right, you can see that there are 3 of, so these graphs can really be not at all isomorphic. And before you even consider the one-to-one correspondence that needs to exist, because once you observe, if they ask if the graphs are isomorphic, you're going to see we need to first observe if the degrees, um, the same number of vertices of a certain degree exist in both graphs, if that is clear enough. Okay, next question. Right, so this is what I was speaking about yesterday. So if you're not asked to draw, yes, please.
Can we go back to the previous question?
Okay, that's fine. Expect these questions tomorrow, multiple choice, y'all. Okay.
We've never done a question where they're asked to draw two isomorphic graphs. So is that would that
Okay.
possibly come out?
Yes, definitely. We can draw two isomorphic graphs.
Can we do an example?
Okay, yes, we can do an example where we draw two isomorphic graphs. Okay, so we have, obviously there are lots of examples we can draw. For example, okay, I mean, I would say let's look at this one here. Like, we can be able to draw two isomorphic graphs like here, that are one way you can move a vertex to get isomorphic graphs. So isomorphic graphs are the easiest to do. Like, you can take this vertex, you can pull this one inside here. So, or you can pull this one such that it sits somewhere here. Okay, if you have this, and then you pull this one in this direction, what is going to happen with that graph? Okay, let's look at that. So you'd have this, for example, and you'd have that, and then you'd have that. So you'd have those vertices there like that, right? And then now you pulled, we're just deliberately just moving the vertices in space, right? So if you move this one and you drag it further enough, so it's going to be sitting somewhere there, for example. Right. So if it's sitting somewhere there, the edges of a graph can cross each other, but not bringing about some vertices. So we can, if you pull this one, so that this edge will run over that one, it's allowed. Right. So and once you have that, then for instance, you'd have that that is there, and now this vertex, you can allow it to sit somewhere here. Okay, something like this. Now, we just moved to the vertices. Can you analyze the degrees of these two graphs? For instance, I mean, if you have what is the degree of this vertex here? Okay, this one is of degree 3. Okay, and this one, so this one is degree 3, and this one is also degree 3. So it's the same degrees as the original, right? Degree 2, degree 2, degree 2. So surely these two graphs here are isomorphic. Okay, but I know that you can draw so many, even like that, but it's easy to draw the isomorphic ones because you just move the vertex. You can just move the vertex in and distort the shape. But in the process of distorting the shape, you're able to get a graph that is isomorphic. Okay, without a lot of reasoning anyway. But that looks like it's different, you know. But also, yeah, the adjacency is preserved, such that the vertices of a given degree that are adjacent here are also adjacent there. For instance, we have that here, the vertices of degree 3 are adjacent vertices. Okay, right. And so here also they're also adjacent. And that is one property of the isomorphic graphs, that the isomorphic graphs preserve adjacency. So you can have another graph, but the adjacent vertices in one graph, the corresponding vertices in one graph, that are adjacent remain adjacent in the next graph. Okay. In particular, isomorphic graphs can be easily seen by just moving vertices and making them look different when they're actually the same. Okay, next question. Right, let's look at the list of, now I was speaking about these yesterday. So you can be given things like degrees, right? So at this point, like the list of degrees, right? The list of degrees of the vertices of a graph arranged in non-decreasing order is called a degree sequence. Look at this. This is a good question. I decided to bring this one because it is so good. Why is it so good? Because it's giving us a definition. They're defining a degree sequence for us so that we can be sure what a degree sequence is. A very rare situation. The list of degrees of the vertices of a graph arranged in non-decreasing order is called a degree sequence. Non-decreasing. So what does it mean to say non-decreasing? Should have, is it the same as saying increasing order? Obviously not, because non-decreasing would mean it can be uniform order. Okay, so like in this case, it can be ones only, vertices of degree 1, right? But now the list of the degrees, so this you can learn, but no one is going to ask you to define anything. We don't ask, in this module, you're not asked to define things, but you're asked to apply the definitions to situations. So the list of the degrees of the vertices of a graph arranged in non-decreasing order is called a degree sequence of the graph. Okay, we here. So let's look at this one. Draw a graph with the degree sequences so they can give us a degree sequence. What is the degree sequence? Is the list of the degrees of the vertices of a graph arranged in non-decreasing order. Okay, so we've just found a new definition there. Right, so let's draw that such a graph. Okay. Okay, This is a very interesting question. Does this one even exist? Right, such a graph. Right, so we note that such a graph does not exist. Why? Does not exist because the vertex this is a very important, interesting example where the graph does not exist. The degree sequence is there, but does not exist. Why? We analyze that to say, why is it that somebody cannot be able to draw such a graph here? Right, such a graph does not exist because the vertex of degree 5 right has to have right has to have 5 neighbors. 5 neighbors. Just right click here. Right is to have 5 neighbors. Right is to have right has to have 5 neighbors while the graph only has 4 vertices. So if you are to supposed to draw a graph with this degree sequence, we see that such a graph does not exist. Why? Such a graph does not exist because the vertex of degree 5 has to have 5 neighbors. This vertex of degree 5 has to have 5 neighbors, while the graph only has 4 vertices. Okay, so that is the point. So this graph cannot exist at all. But very interesting, just to note that. It's a very, very good example. What is the meaning of the description here? Okay, somebody can try to draw the graph and see the kind of challenges you're experiencing. Because if you're supposed to have um, a vertex of degree 5, then it would mean that you have a vertex here, it must be of degree 5. But we can't draw so many edges here because we can see that such a graph does not exist because the vertex of degree 5 has to have 5 neighbors. It must have 5 neighbors. While the graph only has 4 vertices. Right. So if it is 4 vertices, then you can have a vertex, for example, in one attempt. And then now, how is it that this one is degree 5? Because this edge is out. So now attempt to construct this graph or to draw this graph, you can see that no, this one must have degree 5. Okay, then it means that there must be 5 incident edges, but they can't be 5 incident edges because of that. Because this graph is only 4 vertices. 1, 2, 3, 4. So yeah, the 3, 4. These ones 2 are out. Okay, so that is the situation. All right, we continue and look at the next question. Okay, let's look at another example. Now, you need to, in this case, draw two non-isomorphic graphs with the degree sequence triple one. Okay, let me see what you're thinking there.
Can we go back to the previous question? We did something similar and we got this
Yes,
answer.
yes. Okay, that's fine. Let's just look at that. Right. Okay. Right. We're looking at that to see exactly. Yeah, we did a similar question, I remember. Yeah. Right. Trying to open that up. Right. So here we're to draw a graph with degree sequence. So for instance, triple one and triple three, or say why no such graph exists. Right. Obviously, we noted that at this point, if you add the degrees, the sum of the degrees is actually an even number. Okay, thus we are dealing with a graph of size 6. Okay, because it's 2 times the size of the graph. And then this size, what is the size? What does it mean to speak of the size of a graph? Size is the number of the edges of the graph. Right. According to the first theorem of graph theory. Yeah, I was saying according to the first theorem of graph theory, because the first theorem of graph theory says when you add the degrees, you must get twice the size of the graph. And now, if you factor the number 12 to be 2 times a certain number, then the certain number that is multiplied by 2 would therefore be the size or the number of the edges of the graph. For example, so now um, is it possible to construct this one? Yes, it was possible. Why? Because we have 3 variables of degree 3, of degree 1, excuse me. So it's 1, 2, 3. And then we have 3 variables of degree 3 each. So this one is 1, 2, 3, degree 3, 1, 2, 3 edges, degree 3, 1, 2, 3 edges, degree 3. So as a consequence, it's possible therefore to construct this graph up here. Okay, but also because the sum of the edges add to twice an even number. But not only that, but it's a balanced graph because you have enough supply of the vertices. Okay, for example, if we were to drop some vertex here, it would, for instance, if you were to drop a vertex of degree 1 here and make and give an example where you have 2 vertices of degree 1. So you'd have degree 1, then if this one was not there, it was going to bring a challenge because it would not be possible to draw this graph, right? Because now if this one is out, then it means that this vertex here is going to be of degree 2. And if we want to force it to be of degree 3, we can't, because um, we would need a vertex for us to draw an edge. Okay, so yeah, um, very interesting questions. Just expect them in the first introductory questions on graph theory. These are the most basic of things you can play around. So you try to construct the graph sometimes and realize that you run into trouble, into a challenge, because maybe you realize, okay, but this can't be constructed because I don't know if I will need more vertices, something like that. Okay, but yeah, but thanks for the question because it's very similar to that. So we constructed that graph there, but this one was good because it had enough vertices for us to construct. But unlike this one here, this one does not. Okay, this one does not. Okay, that's fine. So this one does not. For example, why does it not? It does not because okay, it was the previous one that couldn't. Okay, let's look at this one now. Um, that was B. Okay, I just want to give another example. Okay, I'm gonna give it just here. Okay, let's look at this one first. Right, here we need to draw 2 non-isomorphic graphs with degree sequence that. Is it possible? Well, I mean, the first test is if you add all these, it must be an even number. for us to be in a position to construct the graph. Right. So for instance, if you add this is 3, 6, 10. So yes, it might be possible. It might be possible. So now let's draw two non-isomorphic graphs with this degree sequence. Okay, so you try anything here. You literally try anything, anything. Okay, so we have degree 1, so we can have degree 1. Right, so if you have degree 1, you actually do that. Right, identify that accordingly. So you have degree 1. Here is degree 1. Right, like this. For example, okay, you can always keep trying. Okay, saying degree 1, then you do degree 1. Okay, so you have degree 1, degree 1, degree 1. Now you can drop this one here. To meet this one, so that this one is degree 1, degree 1, degree 1, degree 3. And then you can just put this ones here. So degree 2, degree 2. And, okay, I need to avoid, we need to avoid labeling these degrees. Okay, so we avoid labeling these degrees. Okay, why do we avoid? Because now normally the labels have meaning. They mean the vertices themselves. So if you put a 1, if we put numbers here, they mean it's vertex 1. It doesn't mean it's actually the degree. So we don't write degrees like that. Right. Now, here's another one. So we can do 1, 2, 3, 4, like that. So you can do this. This is degree 1, degree 1. So this would be a disconnected graph. Disconnected. So you have vertex here, an edge there, an edge here, and an edge there. Okay, so we have these two non-isomorphic graphs with degree sequence that. Um, So, I mean, these two graphs, are they isomorphic? Because we're supposed to draw, what is the instruction? Draw two non-isomorphic graphs with a degree sequence. Does this one have the degree sequence? Okay, this one has degree 1, degree 1. So there are 3 vertices of degree 1, degree 2, degree 2. There are 2 vertices of degree 2 and a vertex of degree 3. Um, right, so here, this one here has 2 vertices of degree, there's degree 1, degree 1, and then degree 1. So there are 3 vertices of degree 1 in this graph. But now, very important example of a graph that is disconnected. So you have like 2 pieces that you can draw, but that constitute a single graph. Also, now you look at the degrees. So here you have degree 2, and then degree 3. 1, 2, 3. So yeah, so this graph and this graph are clearly non-isomorphic. Why would they be not isomorphic? You need to obviously observe that, observe adjacency. That in this graph, for instance, the vertex of degree 3 is adjacent to the vertices of degree 2, right? But here, let's check the vertex of degree 3. Is it adjacent to the vertices of degree 2? Right, so there's a vertex of degree 2 there, there's a vertex of degree 2 there. Right. Um, Now you note also one other thing. Would a vertex of degree 3 is actually here adjacent to a vertex of degree 1. Right. So also here vertex of degree 3 is adjacent to vertex of degree 1. Right. But also now you observe vertex adjacency. If you are to look at whether a one-to-one correspondence can be given. Okay, here the vertex of degree 2, each vertex of degree 2 is adjacent to a vertex of degree 1 and a vertex of degree 3. Let's look at the vertex of degree 2 here. Must be adjacent to, if they were to be isomorphic, a vertex of degree 2 must have the same neighbors of the same degrees. But here, this vertex of degree 2 has a neighbor of degree 1, um, has an adjacent vertex. That's the word we use. Has an adjacent vertex of degree 1, adjacent vertex of degree 3. But here, there's a vertex of degree 2. It's not having a neighbor, it's having a neighbor of degree 3, okay. But is it having a neighbor of degree 1? This vertex of degree 2 is not. This vertex of degree 2 is not adjacent to vertex of degree 1. Right. So with that observation, because even this vertex of degree 2 is not adjacent to this vertex, because adjacency means there must be an edge that links them. Then those vertices are what? Are adjacent. All right. So with these two graphs, therefore qualify to be non-isomorphic graphs. Right. I want to give also another example. Right. Here's another example. In this example, we ask the question. So the students must be able to draw. Here's an example. They must be able to draw a graph with degree. With degree sequence. Draw a graph with degree sequence. Right. So if we just give another example here. Okay, if we want to 5 of the ones, 2, 4, 5 of the ones, and then a 5. Right. Or say why no such graph exists. Okay, we continue. Right, draw a graph with degree sequence that will say why no such graph exists. 2, 4, 5. Okay, first and foremost, now according to the first theorem of graph theory, some of the degrees of a graph must be twice the number of the edges for the graph um, to be possible to construct, to be constructible. So obviously here you can see that if you add the 5 ones and this one, it gives 10, which is 2 by 5. So you can draw a graph of size, potentially of size 5, because it's 10. This is 10, and then 10 is 2 by 5. Right. So now can this be constructed? Let's see. So you have a vertex here. Right. You have vertex here. Right. Right. Let's see what we have here. Right. So you can have a vertex there like that. It must have degree 5. You must have one vertex of degree 5. So 1, 2, 3, 4, 5. These vertex must have degree 5. By good luck, then we have these ones, other ones of degree 1, which are 5 of them. So it becomes so possible to easily construct the graph. It becomes possible to just what? Easily construct the graph. So yes, we can be in a position to construct this graph there. Okay. Right. So let's look at some more examples. Sketch. Let's sketch again. Right. You must be able to sketch two non-isomorphic disconnected graphs on 8 vertices with each vertex of degree 2. Explain why your two graphs are non-isomorphic. Okay, how do we answer this question? We have learned a lot. And one would just think that we know how to draw pretty much. We understand how to construct a graph, what graphs are constructible when the sum of the degrees are an even number, and then we can write them as 2 by the size of the graph. Now, is this one possible to sketch two non-isomorphic disconnected graphs on 8 vertices? Okay, disconnected, but now non-isomorphic. Okay, the word disconnected is coming in. I used the word disconnected at some point for one graph we drew that was in pieces. So the formal word obviously is disconnected. But these graphs themselves must be non-isomorphic, but they must be on 8 vertices with each vertex of degree 2. Let's start. Now we can do this. Okay, so we draw this. Vertices of degree 3. Okay, this one, it's K3. Okay, it's a complete graph on 3 vertices. Right, so but what we need 8 of them, so we can do 5 more because it must be disconnected. So disconnected means that the graph must be 2 pieces of graphs, 2 pieces of graphs. Okay, so but we just need the graphs to be on 8 vertices. That's all. So surely these two graphs are on 8 vertices. 3 by plus 5 is 8. Right, so that is the one we drew, and we drew another one. But this one is just one graph, actually, but it's said to be a disconnected graph. Right, so you can have another one on 4 vertices, like this. Like this. Um, so also this one is 4 vertices, so we have 8 vertices. So yes, these are the kinds of graphs. Disconnected, okay, with each vertex of degree 2. Very important extra condition. Each vertex of degree 2. You can see here degree 2, degree 2, degree 2. Each one is of degree 2. So this and also is on 8 vertices. Each or 8 vertices, 8 vertices. They did not. They were not specific when it comes to. But they said we need to explain. We need to explain why. The two graphs are what? We need to explain why the two graphs are not isomorphic. Okay, so we continue. So we continue. Right. So we have that. We have that. Right. So we have explain, explain. Um, we need to explain why your two graphs are non-isomorphic, so they can ask you to explain. So let's explain. Right. So because by explaining, we understand the graphs more in the process. Right. The two graphs are non-isomorphic. The two graphs are non-isomorphic because the first graph, consists of a three-circuit. Because the first graph consists of this is a 3 second, this is a 5 second, but this one is 2 4 seconds. Right, so it consists of a 3 second and a 5 second. Right, the first graph consists of a 3 second and a 5 second. while the second graph consists of two. Consists of two. Four seconds. Okay, this one now consists of 4 seconds, so they're not isomorphic because of that. So in other words, what is the meaning of this example here? This one is saying to us, you can have the vertices of a given degree that are adjacent accordingly. Like in this point, every vertex is of degree 2, and the vertices of degree 2 are adjacent to each other. Each vertex of degree 2 is adjacent to two other vertices of degree 2. But now, because that is not enough, it's not enough to justify, because you still can have the degrees that are the same, but now the graphs are not isomorphic. How? This explains the notion of using the circuits. Okay, so if you realize that, okay, you have the degrees that are the same, um, then you come to the circuits. Yes, please. You have a question? No question.
What is disconnected?
Oh, yes.
What is disconnected? The what?
Disconnected, yes. Disconnected means that
Uh,
the graph is not continuous. It consists of separate pieces of graphs, or it's actually constituted by separate subgraphs. And obviously, these are called subgraphs, like subsets. So this is a subgraph, another subgraph, but they both constitute a graph, and now they're disconnected. So it's actually a very good way to just emphasize the use of the word disconnected in the case of graphs, because these two are disconnected. They are one graph, but disconnected because we can see that there's no edge that connects the two subgraphs up here. The same applies to obviously these two graphs here. And these graphs are in each case actually disconnected. Okay, let's look at more graph examples. Okay, these cover the basics on the graphs. Okay, let's draw the complement. We looked at the complement last time, but let's understand the complement more. How do we find the complement of this one? Right. So the complement, draw the complement of this graph. So the complement is given by, what is the complement given by? So at this point, then to draw the complement, we normally just draw the vertices first. So we draw the vertices first. After having drawn the vertices, then we connect the vertices that were not connected there. Okay. So how do we do that? So like there was no edge here. So you can draw an edge here. Similarly, there was no edge here. You can draw an edge there like that. There was no edge there. You can draw an edge here. There was no edge here. You draw an edge there like that. Like that, okay? What is next? Okay, now more edges. For instance, after this, we've actually drawn an edge here, but there was no edge there as well. So we can draw an edge here, like that. Similarly, um, we have an edge here. We can draw another edge here, like that. Right. Let me see now. Anything else? Right, that's all. It looks that way. Right, so obviously it looks like it is all. So we have, therefore, the complement is given by that one there. We looked at the complement last time, but I brought this one because it's quite a very simple one to draw. It doesn't have lots of edges. So I decided that we just recap on the notion of the complement, but by looking at um, uh, an easier graph to draw. Next question. Okay, tomorrow, obviously, you'll be seeing graphs like this, normally at the beginning of the exam. Right, the things looked at on the degrees, degree sequences and things, and drawing graphs, normally obviously appear at the beginning, but sometimes they don't even appear at all. And you can just, in the exam, come across this one as your very first question. And now these will say, determine whether the following two graphs are isomorphic or not. If they are, give a vertex correspondence. So if they're isomorphic, then we must be able to give vertex correspondence. If they are not, then give a reason why. Okay, let's analyze this. First and foremost, are they isomorphic, these two graphs, or not? Okay, these two graphs look like this one has just been rotated. Looks that way, something like that, anyhow. This component appears to be so they're tempting to actually make somebody think um they're tempting to make somebody think that they're actually isomorphic graphs, but we realize that these two graphs are not isomorphic, right? The two graphs, right? We note that the two graphs are not isomorphic. Why? Why? It's not enough to just say they're either isomorphic or not. We need to substantiate. Right, the first graph. Here's the reason. The first graph. The first graph has 4. Has 4 3 seconds. Has 4 3 seconds. What are the 3 seconds? Okay, we're gonna um, state them here. So we can look at the second 1, 5. So we go from 1 to 5 in view of the first graph, 1 to 5. Then you go to 6. After 6, we go to back to 1. So that is a 3 second, this one here. 1, 5, 6, 1. Okay. Let's look at another 3 second to see if they have the same 3 seconds. 3 seconds will be the easiest ones because there are too many triangles in this case. So they are the easiest ones to first try to compare. Um, Obviously. Okay. Right. Next. There's another one. Vertex 5. You go to 6. You go to 7. Back to 5. So we have taken this one and now we're taking this one. So 5, 6, 7, then 5. So we found another 3 second, but are they the same number? If you can exhaust all the 3 seconds here, there must be the same number there. Right, there's another one. 5, 7, 4, 5. 5, 7, 4, 5. 5, 7, 4, 5. So that is also another 3 second. And 2, 3, 8, 2. 2, 3, 8, 2. Okay, we have somehow exhausted them because somebody can just say we have a 3 second here, one, we have another 3 second there, we have a 3 second there, and we have a 3 second there. So we can easily see the first graph is for 3 seconds. Okay, so it's easier to see. Right, so this one, there is one here, there is two there, there's three there. You can see that, so it's easy to realize that this one has sort of those 3 seconds is sort of three triangles there. And that is enough to say the two graphs are therefore not isomorphic. Okay, very interesting example here. Because sometimes it can take time to see if the graphs are, some graphs are very subtle and they might not be isomorphic, whereas they're attempting to think that, to make somebody think they're isomorphic. While the second graph, while the second graph only has only has three. It has 3 seconds. Yeah, you see, 1, 2, 3. Okay, let's list them because there are not so many. Right, you start with A, E, F, A. A, E, F, A. Okay, come to the second one, G. G, B, H, G. G, B, H, G. Next, H, G, B, dash. H, B, C, H. So, um, we've just easily listed the 3 seconds, and therefore these two graphs are not isomorphic. Very, very important observation. And now, obviously, one can look at also the experience we've acquired to show that two graphs are not isomorphic, because the truth is, um, we use examples in mathematics to learn. From definitions, we build examples, and from examples, even theory is built. Theory is built by examples because when we observe, the examples normally demonstrate a pattern. From the pattern, we even develop more theorems that constitute theories. Okay, next question. For and hence, the two graphs are not isomorphic, and we've stated why. Okay, I made space available there. Proves that the graph below does not contain a Hamilton second. Right, so we're gonna prove this one. We're gonna prove this one. Right, so let's look at it together. How to even look at this graph here? And how do we prove this here? How do we even prove this here? Okay, so we're gonna look at these and attempt to prove these together. Right, and attempt to prove these together. Right, 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 right. Okay, so just note that, note that, note that, note that, note that, note that. Okay, what is a Hamilton second first? We define. All right, Hamilton Hamilton circuits and paths right are circuits and paths are secant and paths. Right, these are secant and paths. Right, that visit each vertex, in a graph, in a graph, exactly once. Exactly once. Right, Hamilton seconds and paths are seconds and paths that visit each vertex in a graph exactly once. So note that. So we continue. We continue. Prove that the graph below does not contain Hamilton second. Let's prove this. How do we even prove this? Too easy to prove. Right, here's a solution to the question. Right, what is the solution to this question? Since the vertices C and D are both of degree 2, we have to use the edges BC and CE for vertex C. Okay, we're going to analyze this together for vertex C as well as the edges BD and DE for vertex D. Okay. Okay, well, I will explain this. This is called rule 1 of the Hamilton seconds. But then right, but then we have a proper subsecond with a proper subsecond. The proper subsecond, if you start BC, BCE, DB. We have a proper subsecond BCB. With a proper subsecond contradicting contradicting rule 2. Okay, rule 2, what does rule 2 say? Rule 2 say there must be no proper subsecond. That is rule 2. So rule 2 says there must be no proper subsecond, but there is a proper subsecond here. What is a proper subsecond? Well, a proper set, a proper subset from set theory um, is actually different from an improper. Well, improper would mean it equals the whole thing. For example, if one says A is a subset of B, okay, so this one is proper because it's smaller than the set B, right? So, but if you look very carefully, um, if you look very carefully, you realize then that um, this one is improper. This one, if this like this, is improper. Like that. So anyhow, right. So what does rule 1 say? Right. Since the vertices C and D are both of degree 2, let's look at the vertices C and D. We need to analyze that. So if you look at the vertices C and D are both of degree 2, we have to use the edges B, C, and CE, right? B, C, and CE for vertex C. B, C, and C for vertex C, as well as the edges BD and DE. BD and DE for vertex D. That is certainly rule 1. What does rule 1 say, actually, of the rule 1 of the Hamilton seconds? What does it say? Right, we analyze that. Here is what rule 1 says. If a vertex X has degree 2, both of the edges incident, okay, so both of the edges incident, both of the edges incident to X must be part of any Hamilton second. Okay. If a vertex X has degree 2, both of the edges incident to X must be part of any Hamilton second. Let's look at now. We are seeing here that since the vertices C and D are both of degree 2, if a vertex X has degree 2, both of the edges incident to X must be part of any Hamilton second. So there is this one of degree 2. So both of the edges incident to this must be part of a Hamilton second. So since the vertices C and D are both of degree 2, we have to use the edges BC and what? And CD. So now we're then saying these edges incident to X must be part of a Hamilton second. So we use the edges BC and CD. Right. As well as the edges BD and what? BD and DE for vertex D. That is rule 1. But then we have a proper subsecond contradicting rule 2. If we use these edges here, then this becomes a proper subsecond. What is a proper subsecond? It is a second not containing all the vertices, right, can be formed when building a Hamilton second. A proper subsecond is a second not containing all the vertices, right? So that is the fact, that's the reason particularly that we have that this graph here does not contain a Hamilton second. So think of these and make sure you sort of understand in view of the rules. Right, but I think that I'm going to state the rules for Hamilton seconds there. Here are the rules. Here are the rules. Right. These are called the three. Right. These are called the three rules. What is rule 1? Three rules for Hamilton seconds. Right. What are the three rules for Hamilton seconds? We analyze them now. There are three rules for Hamilton seconds. What is rule number 1? I'm just want to state them so that you can have all the rules in full, and then we're going to move on to the other things. Right, because these Hamilton seconds are very important, but they're a little bit tricky sometimes. So you need to uh, have the rules at uh, one's disposal. So let's state the rules. So what does rule 1 say? It actually says that if a vertex, right, if a vertex X has degree 2,
Hello.
yes, please. Please
Can we
continue.
skip the rules? I already have a
Okay,
screenshot of the.
all right, all of the rules. Okay, that's fine, that's fine, that's fine. All right, good. Let's just keep them and let's just move on. Thank you. Particularly, I stated that. Right, let's put another example now that is about more graphs. Right, in view of this second chord method, let's look at this particular problem. Right, second chord method and planarity and planar graphs. Right, use the second chord method to determine whether the graph below is planar. Okay, this you can expect to find tomorrow. Right, if it is, give a planar drawing If it is not, find a K33 or a K5 configuration. Okay, we discussed this and I want us to discuss this because it's extremely important there, but it's way too easy there. And I've made the graph available at the back. Okay, how do we analyze this graph and how do we give a planar drawing of these here? How do we give a planar drawing of these? So we think about these together. Right. So first things first, what is the first thing that we do always? We identify a Hamilton second. So we use the Hamilton second. Right. So we're gonna use the Hamilton second 1, 5, 6, 2, 3, 7, um, 8, um, 4, 1. Okay, let's start. 1, 5, 6. Okay, we're just looking at Hamilton second that visits all the vertices. 6, then 2, then 3, then 7, then 8, then 4, then 1. Okay, so we use the Hamilton. So we use the Hamilton second, that one. First, we choose the Hamilton second because it visits all of them. How sure are we that it visits all of them? So you have up to 5, you have 6, you have 2. It doesn't matter what you choose, right? But it must visit every every vertex once, right? You have 2, then from there you have 3, you have 7, you have 8, you have 4, and then you have 1, like this. So surely these visits all the vertices, so it qualifies to be Hamilton second, but it begins from 1 and it ends at 1, and hence a second, not just a path that actually ends anywhere else. Right, now, by inside-outside symmetry, by um, outside symmetry, outside symmetry, we choose 1, 2 to be, okay, inside. So we're going to do this. We're going to draw a circle like this. And then we position 1, 5, 6, 2. I'm just putting these vertices here in that sequence. 2, then there's 3, then 7, then 8, then 4, then 1. Okay. So with this is the Hamilton second, and we have, because it visits all the it's a second that visits all the vertices of the graph. And then now we have put the vertices over there. Okay, good. Let's see what else we have. All right. So by inside-outside symmetry, we choose 1, 2, um, to be inside. Full stop. Right. So in other words, now we choose 1, 2 to be inside. So we have 1, 2 because it's the first one. Right. So after that, what do we do? Then we continue. Okay, there are certain things we call codes, and I want to mention the idea of a code. And as far as we know a code from school, right? So, but there are certain codes that you need to uh, note. Okay, there are certain codes that you need to understand. Right. So when I speak of codes in this case, right, we're going to speak of codes in this case. All right, but let's continue first. So we choose 1, 2 by inside outside symmetry. You choose 1, 2 to be inside. Then we continue with the process. Right, we continue with the process. Then 5, 7 has to be outside. Has to be outside. Right. So now 5, 7 has to be outside. Now let's look at that one. Right. So if you look at 5, 7, right. So because now if you draw 5, 7, it has to be outside. Why? Because it's gonna cross. So if we draw it from here to there, it's gonna cross. So we need to draw it outside to avoid crossing in our attempt to see if it's really planar or not. So we avoid crossing. So 5, 7, you can do this. Okay. Then 6, 8. Okay, now we look at 6, 8. Where is 6, 8? Right, 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 right. Okay, then 6, 8. 6, 8 cannot be drawn. Okay, let's look at 6, 8. Right, if you draw like this, it's gonna cross, but also if you draw outside like this, it's also gonna cross. So we can see therefore that 6, 8 cannot be drawn. Um, hence, so if you look at 6, 8, so 6, 8, we can make it dashed like this. Hence, the graph is not planar. Right, after this, the following is a K33 configuration. The K33 configuration is a K33 configuration. Okay, so what do we have of the graph? Goodness me, right, so of the graph. Now let's see what this one. Right, configuration of the graph. The following is a K33 configuration of the graph. What is the K33 configuration of the graph? Right, right. Mm-hmm. Okay, okay. We continue. Right, so we draw this. One, two, three. Right, one, two, three. Then we have one, two, three. Okay, then do this. We have this. Right, so um, then you have this with that. There you have this, and then you have that. So you have 176, vertex 1, vertex 7, vertex 6, vertex 2, vertex 5, vertex 8. And then you have vertex 3, and then you have vertex 4, like that. All right, so we have this. This one is a K33 configuration because K33 means what? It's without the dots in the middle um, of the edges. But once you put the dots there, they become, you actually therefore have a configuration. But I want us to analyze this very carefully because in view of the Hamilton circuit we chose in the beginning, so you have that 1 goes to 5, goes to 6, right? And goes to 2, right? From 2, we go to 3. From 3, we go to 7. From 7,
Hello.
yes, please.
How did you get this 176258?
Yes, okay,
How did you, why did you put it like that?
yes, okay, that's a good question. Let's just discuss how that is first and foremost achieved. Right, so first and foremost, what you need to realize is the fact that we actually desire from these a K33 configuration, or a K33 configuration, um, because we have already seen that is non-planar, and therefore we need three vertices. Right, so if we need three vertices, we focus on the Hamilton circuit. Right, from the Hamilton circuit, we realize that we need a set of 6 vertices, and these 6 vertices themselves must actually be vertices that are part of the original graph. So for example, we start with the original, with this first vertex we chose in our Hamilton circuit, vertex 1. Right, and then now 1 goes to 5. And you can see it goes to 5, and that gives us one more vertex at the bottom, and we go down diagonally. Right, and then after that, we have that 5 goes to 6. So 5 will go to 6. So first we just position the dots 3, 3, and then now we just trace, we just circulate this Hamilton circuit. So if you put 3, 3, because we're speaking about a K33 configuration, then you start saying, okay, 1 goes to 5, then 5 goes to 6. You put this one, right? And then from 6, you need to go to 2, right? So from 6, we go to 2, right? And then from 2, you go to 3, like that. And then from 3, you must go to 7. And then when you get to 7, from 7, you must go to 8. So from 7, you need to go to 8. So you need to obviously just look at the pattern and how we just run through these. Because from 7, you go to 8. So 8. Now, obviously, if you're at 7, then you can think, can 8 be here or there? Okay, so obviously it must form this second at the end of the day. So 7 goes to 8. Then from 8, you go to 4. Right. And then from 4, you go back to 1. So in other words, it is actually these that has been rewritten to form this K33 graph. But how do we position the 2, the 5, and that? First, we need to put the 3 dots and then just follow accordingly. How do we just move normally? So we have this path we trace always, right? So we move from 1 to 5, then from here to there, we go to 6. Always do this. Right, when you get to 6 now, you need to move. Right, and the practice is to move from a 6 that is here to a 2. And then we sort of go back because from 6, then you go back to just below 1, and then you go to 3, and then you go to 7. Then you sort of go back now to where you came from at the extreme, just below 6, you get an 8. So that is how we get. But first, you just put the 3 dots, 3, 3. And now not only the 3 dots, but you need to be able to draw the K33 always. Okay, so first you just draw the K33. Okay, what is the K33? The complete graph on 6 vertices, 3, 3 at top. So you put this one, that one. So you put 1, 2, 3, 4, 5, 6. Okay, so we do this. Right, so when you do this, that is the K33. So we do what? We connect this one, we connect this one, we connect this one. So you must draw this K33 and then just put the vertices there. So, but how do you draw it? You must just learn how to draw it because it's always the same, K33. Right, so it's always like this. Then you go like that, right? And then you go this way, and then you go from here to there, from here to there, right? See now, this one goes from here to there. This one goes from here to there. Okay, 3. Okay, we have that. So this is a K33 graph. Then what do we do then? We just draw this K33 without these numbers, without the vertex labels. And now we therefore are able to trace. But now you look at the path, the way we move up there, that you start from 1, then you go to 5, then you go to 6. You go like V. You take the shape V. Following this sequence, you put the numbers there. Okay, that's just the idea. Right. Now, but also I want to mention there's certain things we call, because this is called the second chord method. This is called the second chord method. So there are certain things, therefore, we call chords. Right. So, right. So you choose a second, a Hamilton second, like we saw. Then you pick um, um, a chord to draw. Right. You pick a chord to draw. How do you pick a chord? Like you chose this Hamilton second. We chose this one. After we chose this Hamilton second, then we pick we did what? We picked, we picked um a chord, right? We picked a chord. What is a chord here? Actually, given this graph, what would qualify as a chord and what would not? And that's what I want to drive at here, right? So we pick our first chord to draw, right? And then our first chord was, for instance, um, we chose 1, 2, right? We chose 1, 2 to draw because 1, 2 is an edge in our graph. 1, 2 is an edge in our graph. But if 1, 2 is an edge in our graph, we can pick it. But then 1, 2, it becomes a chord in the circle. It becomes a chord in the circle. So because we drew the 1, 2 there, but it is, in other words, you really can see that 1, 2 is an edge, a graph, but obviously as drawn there, it's a chord. But if you look at 1, 2 in these here, in the Hamilton second, it's something else. The 1, 2 is not just successive vertices in the Hamilton second. Okay, just note that. We continue. Okay, for the graph G below, we determine this, right? So the chromatic number of G, you give a minimal coloring and prove that a similar number of colors is not possible. Okay, we recap on the chromatic number. We looked at the chromatic number, but let's just recap on it. Right, so what is the chromatic number of this graph here? Let's spend some time on as we reason. Okay, first we note that the graph contains triangles. The graph contains triangles so that the chromatic number is at least 3 because it contains triangles and a triangle has 3 colors, different colors. I mean, the chromatic number of a triangle is 3, but it's at least it's 3 or more here because we have just more than triangles, right? So what is the next thing that we do? Next, we try. We try to color the graph with three colors. Because we can see triangles, we try to color these with 3 colors. Okay, the triangles are easier, but yeah, there are other things um, that you can use here. I'm going to explain another method as well that you can use. Right. For the triangle, for the triangle A, for the triangle ABGA, we color A blue, G red, and B green. Then since, okay, so we call this one red. Um, G, no, I'm saying we color A blue. They just use a different color, otherwise there's going to be some confusion here. Okay, yeah, we color A blue. That's what we're saying here. So we color this one blue. G, we call it red. And B, we call it green. Okay, okay, like that. Then since C is adjacent, okay, hence the word adjacent here. Since C is adjacent to G and BC has to be colored, has to be colored blue. Let's analyze what this means. Okay, for the triangle ABGA, what is the triangle? AGBA. Right, we color A blue, right? We color A blue, G red, and B green. Right, then since C is adjacent to G and BC has to be colored blue. Okay, I want us to refine this and write it correctly. I want us to refine this and write it correctly. Then since C is adjacent to what? KC, we can see it's adjacent to B and G, or to G and B. C has to be colored blue. That's what, can I put maybe a full stop here? Otherwise, there's going to be confusion. Since C is adjacent to that, I need to put a comma because I started with since. Right, since C is adjacent to G and B, C has to be colored blue. So we make it blue. Like this. Goodness me. My goodness. Okay, let's see what you get. Right. Next, we note that for the triangle, we note that for the triangle AEFA, okay, let's look at the triangle AEFA, this one here. Um, the vertices E and F have to be colored. They have to be colored by red and green. Let's look at that one. It has to be colored by red and green. Right. So next we note that next we note that for the triangle AEFA, the vertices E and F have to be colored by red and green. So we can do red, green.
Why is E red and F green?
Okay, that's a good question. Because this is blue. So we need different colors because now we can choose even this, you can make this one green and this red because they cannot be adjacent because adjacent blue cannot be blue. So it must be a different color. Because this one is already blue. We can't make this one blue, but we have two colors that are available. So we can use red and green interchangeably there because this one is blue. Right. So that's the thing. So next we note that for the triangle AEFA, the vertices C and F have to be colored by red and green. Okay. So you can easily, you can also do green and red because if you make this one red, um, these are not adjacent vertices as such because adjacent vertices must have an edge, one edge that connects them. So as a consequence, these are not adjacent vertices. So a person who make this one red is not wrong. Okay, because what is wrong is can be to make this one blue because this one is already blue. So blue adjacent vertices are unacceptable in coloring. Okay, next we continue. Let's see now. Right. Red and green, red and green. But then vertex, vertex D, let's look at now vertex D, it's here, will be adjacent. Okay, first we look at adjacency, will be adjacent. Vertex D will be adjacent to red, green, and blue vertices. Okay, let's look at that one. Where is vertex D? This one is adjacent to what? It's adjacent red, but it's also adjacent green, but it's also adjacent to blue. If we started with the triangle of three colors here, blue, red, and green, can we make D blue? We can't because it's already blue. Okay, we pick from our bucket of colors green, but it's already adjacent green, so we can't make D green. Okay, there's another color red. We can't make it red because so this D forces us to look for another color that is different from the three. And hence now this one suggests we need to look for the fourth color because the three colors surely for this graph are not enough. Right, so we can therefore, because it's a question like this, or a couple of questions like this tomorrow, we can therefore not But generally, you don't need to explain like this a lot. You need to be very brief in the way. You need to say the chromatic number. So you need to say there's a triangle, and so the chromatic number is at least 3. And then you start coloring this and say, you can write a list like this. Let A be blue, red, B green, and so on. So it doesn't really have to be, you can even change the presentation, but it's just that normally is written like this for clarity when during discussions. But you can write the things, tables. We can use tables to do this. Okay, we're going to look at that. We can therefore color, not color the vertices with only with only 3 colors. Okay. Hence, we can therefore note color with 3. Hence, the chromatic number of G is 4 or more, at least 4. We now give we now give a 4 coloring of the vertices of the graph. Of the graph. So it means therefore you have blue, red, green, yellow. So we need a 4th color, yellow. Because now the others, the first three are not sufficient. Right. So in other words, we're going to make this one yellow. Right. If you make this one yellow, what color can any of these be take? For instance, you have like the vertex J. What color can the vertex J take? Or what color can the vertex H take? Let's start with H. Right. Look at H. We already have green and red. So can H be blue, for example? Yes, there's nothing wrong with allowing H to be blue because it's not adjacent to any color. So we come to this observation here. So we can make the blue ones, we can make um, A, C, J. Okay, A, C, um, J. Even J, you can make it blue. Doesn't matter. You choose this. It's quite subjective, but it must not contradict. It must not have two adjacent vertices having the same color. Red, you can choose vertex F, G, and I. Okay, so you can make this one red, but you could also make G red. You can also make F red. Let me see. Yes, it doesn't matter anyway. So, okay, let me see. We made F green. So in view of our choice, if you make F green, you put it here and you remove it, doesn't matter. But make sure you have all the vertices at the end of the day. Okay, so you can have, because we just made F green. Okay. What else do we have here? What can H be? Let's look at that. From our bucket of colors. Okay, if we choose this one, E. Is E, what color is E? E is red. Okay, you put E red. Then what's green? Right, so you have F is green, but also you have B is green. Right? What about H? Right, we can choose H to be what? Right, because we've already chosen this one to be green, red. So if it's green and red, here you can use what? You can use any of the colors. Right, so if you choose green and red, you are tempted to make this one blue. But obviously, you need to be very careful to do that. Right, suppose you make H blue. Suppose you make H green. Just a minute. E is, can I just do this? Okay, because now you can have these colors just running around. Doesn't really matter what you do. Right, I think this is going to be easier. If I make, I want to synchronize everything to make sure we don't have colors that are mixed up. So if you make E green and you make F red, you make E green and you make F red. Okay, what would this? Okay, then we come back here. Hey, let me just remove and make sure that we organize the colors well here in the table, because you must write this to this table of the colors to indicate which vertex is what. Right, so if you have that, let's see quickly, please. Right, so you have A is blue. Right, so you have that A is blue from the diagram. So we put it here from the thing, from the graph. Right, C is also blue. Okay, that's correct. J is also blue. Good, because you've chosen J blue. Okay, you can choose anyhow, but every color, every vertex must be colored. Right, red. F is red. Good, I've chosen F to be red. G is what? Right, G is also red. Good. I. I is red. All right. Then green. B is green. Also, E is green. Also, H is green. Now we're choosing H to be green, so we make this one green. So if H is green, right? Once you choose H to be green, then you can see that you can allow this one to be blue red. Okay. Let's see now what we're getting out of this. Yellow is D. Okay. So what is the conclusion out of everything here now? Here comes the conclusion, and the conclusion is These for coloring these for coloring shows that chi of G, which is the chromatic number of G, is 4 or less. Okay, so we needed 4 colors or less. And it follows that the chromatic number of G is therefore 4. It's therefore 4, and we've answered this question there. Okay, we've answered this question there. All right, next question. Right, so in this question, we need to determine whether this graph G is bipartite or not. Is it bipartite or not? State any theorems used. Well, it is not. We'll give the reasons, please. It is not. It is not bipartite because it contains odd decades, e.g., ABGA. Let's look at that one. It's not bipartite because it contains odd circuits. Let's look at that one. If you look at A, B, G, A, it has some triangles, right, which are odd circuits or circuits of odd length. Okay, there's a theorem called Theorem 2. Theorem 2 of our reference tracker. We say a graph V is bipartite if and only if and only if every circuit in G is of even length. It is not bipartite because it contains odd circuits. There's a theorem too that says a graph G is bipartite. Okay, this is very important. What kind of a graph is bipartite? It is bipartite even only if every circuit is of even length. But here we have found a circuit of odd length, of length 3, this one. Or it is, this one is of size 3. How is this one of size 3? The size of a graph is determined by the number of the edges of the graph. So if the edges are 3, then the size is 3. Okay, so obviously it's a subgraph, this one, or just a subset of the graph there. I think maybe it's enough. I'm looking at the time. I can just do some questions. Okay, let's do this one. It's easy as well. Right, determine the number of the 20-digit sequences of the letters of the alphabet The alphabet is 26 letters. Right, so determine the number of 20-digit sequences of the letters of the alphabet, with each letter occurring at most once. Okay, to answer this question, we note that since each letter occurs at most once, at most once, we have an arrangement. We have an arrangement without repetition. That's the answer. The answer is, since each letter occurs at most once, so either it occurs once or it does not occur at all. So the answer is that it is the permutation. We're looking at the permutation of 26 letters taking 20 at a time, because we're looking at the 20-digit sequences. Permutation of 26 letters taking 20 at a time. And then what do we get? Which is 26 times 25 times and so on times 7. So this is exactly what we are getting, because we are speaking about the 20-digit sequences. So this is going to give us 20, because this means that we have 20 places here. Because there's place 1, there's place 2, and then there's place 20. Right, so, but this can also be written as follows. Can also be written as 26 factorial divided by 6 factorial, which is exactly that. The reason is 26 factorial divided by 6 factorial, obviously is 26, 25 up to 7, then 6 factorial, you divide by 6 factorial, and 6 factorial cancels, so is that then up to 7. So that's the answer. Right, so I think that it's some good time for us to say it's a good evening. So yeah, the assessment tomorrow is there at the appointed time. So I think that you need to think carefully and realize what